Hello everyone! Welcome to our Summer of HPC project presentation. We are Athanasios Kastoras and Kevser Ildes, and we will talk about our work on the project Precision-Based Differential Checkpointing for HPC Applications. High-performance computing systems are built from highly reliable components, but by increasing the computing nodes, the likelihood of failure becomes a serious issue. Nowadays, the mean time between failures of a large-scale HPC system is about a day, which means that approximately once a day, the system faces a failure. Of course, all processes running during the failure will be killed, and their data will be lost. This can be devastating on large-scale applications, which may execute for days, weeks, or even months. Therefore, the development of fault-tolerance mechanisms is necessary to be able to protect the application and continue improving HPC performance. Between the several fault tolerance techniques, checkpoint restart is a common one. It suggests taking snapshots of the application at specific times and saving them in stable storage, so that in case of a failure, the execution can restart from the last checkpoint. The disadvantage of this method is that in large-scale applications, there is an enormous number of data to be stored, and due to the file system's bandwidth restrictions, there is a high risk of creating a bottleneck and dramatically increase the processing time. There are some advanced techniques to fight such limitations, such as multi-level and differential checkpointing.
Fault tolerance interface is an application-level checkpointing library which allows users to protect selected datasets using the checkpoint and restart method. There are different checkpoint levels, which are Level 1, it's for local checkpointing on nodes and it's fast and efficient against soft and transient errors. Next, Level 2 uses copy to the neighbor node as a plus to the Level 1 and it can tolerate any single node crash in the system. In Level 3, read-Solomon encoding is provided additionally and it can tolerate correlated failures affecting multiple nodes. Level 4 is flush of the checkpoints to the parallel file system and tolerates catastrophic failures such as power failures. Then, for the differential checkpointing, alpha DCP level is used, and in differential checkpointing, instead of storing all the data in every checkpoint, they are stored once, and then only the differences from the new data are updated, thus decreasing the quantity of data that are transferred. We can also see the difference between approaches in this diagram.
During the summer of HPC, we implemented two new mechanisms in FTI: checkpointing with lossy compression and precision-bound differential checkpointing. Lossy compression is simply a method of data compression in which some information may be lost in exchange with increased compression ratio and speed. With larger compression ratio, we decrease the quantity of data we need to store. To add this feature to the FTI, we used the ZFP lossy compression library. From the user scope, to use lossy compression, one must enable the compression in the configuration file and specify the compression block size and tolerance. The block size is used to set a bound, if needed, to the memory allocated for the compression. Tolerance is the maximum numerical error that is tolerated between the original and the decompressed data. It is important that the user specifies a tolerance suited for their application in order to maximize the compression ratio.
The second mechanism is precision-bound differential checkpointing. It allows us to take benefits from DCP share, which shows the difference between checkpoints in percentage. Floating point numbers have three parts: signed bit, mantissa, and exponent. And the idea of precision-bound differential checkpointing is to cap these significant bits of mantissa according to the given precision value. As an example, if the precision value given by the user is 16, precision-bound differential checkpointing truncates last 7 bits, that is, it makes them 0. To use this mechanism, the user should enable precision-bound differential checkpointing in the configuration file and also enter the precision value. Then, he or she should call the checkpoint function specifying the level as PBDCP. As expected, the smaller the precision, the most benefit we can get from DCP share, since the value remains unchanged for a certain interval, but also the larger the RMSE value, which is root mean square error for uncapped and capped values, and it can also be seen in these charts. Next, comparing pure differential checkpointing and precision-bound differential checkpointing, Again, as expected, TCP share is lower in precision band variation checkpoints. That's all about our project for now, but of course we will continue our further tests, and we also aim to publish a detailed paper about it. At the end, we want to thank our supervisors, Kay Keller and Leonardo Boitista Gomez, and coordinators of the program for their helpful attitude and support. Thanks for watching.